in addition to non-uniform surfaces, we have to think about another kind, and that is a closed surface. So let's look at flux. Through a closed. So closed simply means it encloses some volume. So let's first stress that we have a uniform electric field, and one closed surface would be a cube. So let me draw my magic 3D cube here that we have all drawn and thought about in our lives. We can think about what is the flux in this cube, or of the field through this cube. And if you imagine the cube's actually sitting in the plane of the board, then you could start to sort of assign a value of flux for each of the surfaces. You'd say, okay, the E field is always this way. This one has an area this way. This one has an area this way. The bottom underneath has an area that way. This side back here has an area that way. They all have their own area vector, and the surfaces are uniform. They're not curved. You don't have to break them up into tiles because they're already squares. Okay? There's also one coming out the back, like that. 2, 3. Oh, and then of course the front coming out that side. So 6 sides to the square. So for a uniform field, we can think about what is the flux. And you would say, well, let's get all these fluxes here. Let's see. I'm just going to write it on there. This one is going to be phi. There will be a flux there. Its value will be basically E times A, right? Because they're constant. In fact, I'll just write it like that. I'll write the flux here is EA. The flux here is 0 because they're at 90 degrees. The E field's coming this way. This is coming out of the board 90 degrees. Flux is 0. This one also 90 degrees. The flux is 0. This one down here also 90 degrees. Flux is 0 down there. This one, let's see, where are we up to? We have 1, 2, 3, 4. This one pointing back. What is that one? So now we have the E field this way, A this way. So it's negative EA. Negative EA back there. And in the back of the cube. Back here, again, 90 degrees. E field this way, that's into the board. 0 back there. So it looks kind of complicated, but you get the idea. Basically, around these 4 sides, you have no flux because they're all at 90 degrees. The front gives you positive EA. The back gives you negative EA. So the flux is 0. You just add the 6 sides up, and you get 0. Now this, you could geometrically see it was going to be 0 because all the sides are either at 90 degrees or the 2 are opposite. But I can also tell you this. We get rid of the cube, and we replace it with a sphere. Sphere, here's the front side, here's the back side. We can think about the flux of a uniform field through a sphere. And let's see, what are we going to get? Well, you're going to get, if this side has A like this, and it's actually non-uniform, and the A's here go like that, you're going to see that you're going to get negative flux on this side, and you're going to get positive flux on this side. And since it's symmetric, they're going to add up to be 0. You're going to get phi E of that thing is 0. Okay? What if we drew something more complicated? What if I drew some closed blobby thing down here, sort of a tube that ends in sort of like some beautiful, I don't know even how to represent it here, with a cube on top. It looks like a sideways Texas a little bit. What is that going to be? 0. We don't have to do the vector calculus because the flux of a uniform field through any closed surface is always 0. Okay? Closed surfaces always have the area vector sticking out. That's how they're special. An open surface, it's arbitrary which side the A vector goes. Closed surfaces, we always make it stick out. They always have one side, they always have the other side. No matter how complicated they are, if you have a uniform field, the flux will always be 0. Okay? So let's stress this is uniform because here, let's think about if it's non-uniform field. Okay? let's draw a non-uniform field, which I haven't really done yet. You could have small e vectors here. It could all point in one direction, but you could just have it growing as you go to the right. Right? Getting bigger and bigger as you go to the right. To really make that field would require some charge placed in various positions. But we're not worrying about how the field got created. We're just saying that's the field. It's an E field growing in magnitude as you move that way, and it points that way. Let's put a closed surface in here and see what happens. Well, it's a non-uniform field, but it is sort of symmetric. You can think, well, here's the area vectors coming out on this way. Here's the area vectors going that way on this side. So here's the A's over here. Here's the A's over here. Okay? Back when it was uniform, those two things canceled. But here you can see it's actually different. We have small magnitude field giving us our negative flux, and we have a larger magnitude field giving us our positive flux. So in this case, through a closed surface, phi E does not equal 0. The way I've drawn it here, it would be a positive flux because we have bigger field magnitude on that side where we have the area pointing in the same direction. Okay? So if you want rules to memorize, closed surfaces always have 0 flux if the field is uniform, and the field will not always be uniform. They can have a net flux if the field varies in space.